In this video on soil fertility, we'll focus on the decomposition of soil organic matter, or SOM. First, we'll take a glimpse at the sort of global carbon cycle and the sources from the ocean to plant material. And, it's important to not only do we have a hydraulic cycle, but we have this carbon cycle as a planet, and we need to make sure that each step in this is functioning in harmony with all the others. Decomposition of organic matter can vary based on which part we're talking about. So sugars, simple proteins are rapidly decomposed. Then we work down our way down the scale to things like lignins and phenols, which are very slowly decomposed and can last on site for much longer. Aerobic decomposition is an oxidation process. Remember from a chemistry course, this simply means that there's the movement of electrons. And so we have this large carbon chain on the left of our equation, which yields carbon dioxide, water, and energy. Anaerobic decomposition yields, biggest difference in its yields are the methane, the CH4, which is smelly and a much more effective greenhouse gas, so it can increase climate change effects. Anaerobic decomposition can cause toxicity and provides much lower energy outputs than aerobic decomposition. Factors on the rate of decomposition: there are physical factors, the carbon to nitrogen ratio, nitrogen availability around the material, soil ecology, and the lignin content are some of our top 5 rate factors. So physically, location in the soil profile, right on the soil surface, the conditions are highly variable. So if we move down a little bit, have it incorporated into that A horizon, we have a much more consistent contact with soil microbes, consistent soil moisture and aeration, things like that. Dry and wetting cycles, temperature cycles all have an influence. And then the soil organisms present. And then we have particle size. So if we think of a large branch falling on the surface versus a fine root being decomposed and turned over. Carbon to nitrogen ratio. So microbial competition for soil nitrogen. Plant carbon to nitrogen ratio can affect the decay rate and is variable based on nitrogen availability. So green legumes have about 8 to 30 carbon per 1 nitrogen. Something like sawdust can have as much as 500 2 carbon to 1 nitrogen. Microbes are a lot less variable, so they're usually 5 to 10 carbon for every 1 nitrogen. And decay slowly decreases this ratio. So the more extreme it is, sort of the longer it will take to decay. If you think of putting a pile of sawdust or chainsaw material on the soil versus a pile of fresh soybean material, the soybeans will decompose and be unrecognizable much faster than that sawdust would be. In the soil, a typical AP horizon has a carbon nitrogen ratio of 8 to 15 carbon for every 1 nitrogen. Similar climates, there's little variation based on management. Forest horizons can be up to 30 to 40 once cultivated, so changing that forest into agricultural land can decrease that carbon nitrogen ratio down to 12 to 1 sometimes. And so this can cause a loss of organic matter, and then also change the pH and liming requirements, which we spoke about in the previous video. Microbes require a balance of these nutrients, so about 8 carbon per every 1 nitrogen. And so if material is greater than 24 to 1 carbon and nitrogen, it can cause a nitrogen shortage. And when this happens, the introduction of high carbon depletes soluble nitrogen. So that is where we have a situation where the microbes are using the nitrogen for decomposition and taking it out of solution for the plants. So there's no nitrogen that is plant available. So this is what we call a nitrate depression period. So this occurs when decay organisms consume the labile carbon and decrease that carbon to nitrogen ratio until we get down to about a 20-to-1 ratio again, and then nitrates begin to appear and the soil equilibrates. High nitrogen materials, so less than 20 carbon per 1 nitrogen. Nitrogen is plant available throughout the decomposition process. It is a rapid decomposition process full of microbial growth and activity. So part of the total food web, looking at total soil ecology, we have bacteria and fungi active, nematodes, protozoa, earthworms, etc., and nitrogen carbon cycling. So soil management that increases food web complexity equals an enhanced nutrient cycling and nitrogen efficiency. So we want diverse soils that can handle these inputs with different microbes being active at different stages of decomposition at all times. Decomposition of high lignin content material. So high lignin is a poor resource for soil microbes, and this is a part of the reason why there's an accumulation of plant material in colder forests. So colder forests, trees often have higher lignin content. Microbes have less time to act on them, and so we see a buildup of organic matter over time. And in annual versus perennial crops, so annuals need that input immediately. Perennially, a slow release might be more advantageous. So perennial crops often require smaller inputs for a longer time, and so their natural cycle is likely providing enough nutrients for that plant to grow. Annual crops, they only have a very short time to grow before they are terminated, and so they often need higher inputs in